Tonight, we're looking into posts being spread on social media. They claim the James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth.
Sometimes what seems like a coincidence may be more than just luck. Imagine a game of pool. The balls are arranged in a tight triangle, and the player takes a shot. The cue ball strikes and sends the others scattering across the table. In our universe, there are events so improbable that they defy reason. Picture this, a massive object speeding through our solar system, its gravity pulling a planet out of orbit and sending it into the emptiness of interstellar space. But it doesn't end there. It flings two planets together, perfectly aligned, to begin orbiting one another as they drift away into the void. It may seem impossible, but improbability doesn't always equate to impossibility. The James Webb Space Telescope, JWST, has recently made an extraordinary discovery in the Orion Nebula. In the vast expanses where stars are born, it spotted two rogue planets caught in a binary orbit. Each planet has a mass similar to Jupiter, leading to their nickname, Jupiter Mass Binary Objects, or jumbos. And here's the remarkable part. JWST didn't just find one pair, but 40 jumbos, which make up nearly 10% of all the free-floating planets discovered in the nebula. This is not just an unlikely occurrence. It's so puzzling that scientists are questioning whether we might be missing a crucial aspect of how the universe works. It's as if the very foundations of our understanding might need a closer look. One thing is clear. Our understanding of star and planet formation needs to be updated. But how? That question remains unanswered. Jumbos were first spotted in October 2023, when JWST's advanced instruments captured detailed images of the Orion Nebula. While they may exist elsewhere, these planets have been difficult to detect until now due to their small size and the limitations of current detection methods, such as gravitational techniques. Gravitational microlensing has kept them hidden. This phenomenon, in which a star briefly brightens as an object passes in front of it, was predicted by Albert Einstein, who doubted it could ever be observed. Advances in technology have proven him wrong, but microlensing remains unpredictable. It took JWST's exceptional sensitivity to definitively identify the jumbos. These newly discovered planets are young, around 1 million years old, compared to Earth's 4.5 billion years. But it's their behavior that truly puzzles astronomers. Unlike other rogue planets that drift aimlessly or orbit a nearby star, jumbos orbit each other at a distance of about 200 astronomical units, AU, 200 times the distance between Earth and the Sun. This discovery is both perplexing and thrilling. Jumbos challenge our understanding of planetary formation, dynamics, and the nature of the universe. It's clear that the cosmos still has many surprises in store, and with each new discovery, our view of the universe grows. Who knows what wonders are still out there waiting to be uncovered? Binary systems are common in our galaxy, especially among stars. Approximately 1/3 of all stars in the Milky Way are part of binary or higher-order systems, where two or more stars orbit a shared center of gravity. However, the probability of such systems decreases as the size of the objects involved becomes smaller. For example, about 75% of massive stars are in binary systems, and around 50% of stars similar in size to the Sun have a binary companion. But for smaller stars, this likelihood drops to 25%. Objects smaller than brown dwarfs, those with insufficient mass to sustain hydrogen fusion and only 15 to 75 times the size of Jupiter, are thought to rarely, if ever, form binary systems. In fact, it's believed that such configurations should be impossible, as no known mechanism can explain why these objects would pair up. Yet the James Webb Space Telescope, JWST, has challenged this assumption. During its survey of the Orion Nebula, JWST discovered 540 planetary-mass objects smaller than brown dwarfs. Remarkably, 9% of these were in binary pairs, and 2 even formed a triplet system. This discovery contradicts current models of planetary formation and challenges existing probabilities. The high frequency of these Jupiter-mass binary objects, known as jumbos, is especially puzzling. At 9%, their occurrence is far too significant to be dismissed as an anomaly, prompting scientists to rethink how planets and similar objects form. There are two main theories about how jumbos could come into existence, but neither fully aligns with the available data. Planetary systems, especially in their early stages, are highly chaotic. Imagine a young Earth surrounded by molten rock, comets, and other space debris constantly colliding and merging. Over time, dust particles combine into rocks into asteroids, and eventually, fully formed planets. However, not all objects make it through this process. Gravity can cause some material to be ejected from the system entirely, turning them into rogue planets. Even massive planets can be ejected under certain conditions. One theory suggests that our solar system may have once hosted an additional gas giant, which was expelled by the gravitational influence of Jupiter or possibly Saturn. If true, this would highlight the turbulent nature of planetary systems. While rogue planets are thought to number in the billions or even trillions across the galaxy, their presence doesn't account for the 9% of jumbo-forming binaries. The likelihood of two rogue planets being ejected together with the same speed and trajectory, then gravitationally capturing each other, is extremely low. The second theory proposes that jumbos could form directly in interstellar space, much like stars. Just as a star forms when gravity pulls gas and dust together until nuclear fusion ignites, smaller objects might form in the chaotic environment of a nebula, where supernovae and solar winds scatter material, before gravity collects enough mass to form a star. This theory encounters a significant issue known as the opacity limit. As gas and dust collapse under gravity, their gravitational potential energy is converted into heat. For an object to keep growing, it must radiate this heat away. However, as the object becomes denser, it also becomes more opaque, trapping heat and generating pressure that resists further collapse. This creates a lower size limit on what can form, typically no smaller than a brown dwarf. Anything less massive struggles to overcome this physical barrier. In essence, interstellar gas and dust tend to form large objects, unless there is the gravitational influence of a nearby star or an exceptionally dense environment. Without such factors, smaller objects like jumbos are unlikely to form. The discovery of binary jumbos challenges both planetary ejection and direct formation theories, as neither fully explains their high occurrence in the Orion Nebula. Additionally, the presence of triplet systems complicates the situation further. These findings suggest gaps in our understanding of planetary and stellar formation, implying that the mechanisms behind these processes are likely more complex and less understood than previously believed. The jumbos in the Orion Nebula are reshaping astrophysics, and scientists are racing to uncover what this means for our broader understanding of the universe. Are these anomalies unique to the nebula, or could they be hiding elsewhere in the vastness of space? For now, the answers remain elusive. This additional push allows hot gas to overcome its resistance to collapse. However, once this barrier is breached, the momentum accumulated is too great to stop at just forming a planet. Instead, it results in a brown dwarf, or something even larger, or nothing at all. This is the crux of the opacity limit, which sets the lower mass threshold for objects forming in interstellar space. Consequently, scientists are looking for an extra factor that could explain how jumbos, Jupiter-mass binary objects, might emerge despite these limits. A breakthrough in understanding this process could provide a more elegant solution. If something could counteract the opacity limit, planets could form naturally from interstellar matter. If two such objects formed near each other, their mutual gravitational pull could easily lead to stable orbits without needing a star. This theory sidesteps the improbabilities of earlier ideas, such as rogue planets being ejected and then miraculously pairing up. In fact, it even opens the possibility for smaller planets, perhaps even Earth-sized or smaller, to form naturally. Follow the same approach, staying undetected and beyond the reach of even jwst's capabilities. But perhaps the key lies in revisiting an earlier idea. In 2001, long before the discovery of jumbos, astrophysicist Alan P. Boss proposed a theory in the Astrophysical Journal. He suggested that magnetic fields could play a crucial role in planet formation under certain conditions. According to his model, interstellar magnetic fields might eject a Jupiter-sized object from a collapsing cloud that would otherwise form a brown dwarf or star. The smaller planet-mass object would remain intact, while the rest of the cloud collapsed into a larger celestial body. At the time, this theory was speculative, with no observational evidence to support it. Yet, it's intriguing that the sizes Boss predicted match the jumbos observed by jwst decades later. Maybe these jumbos aren't as unexpected as we once thought. Perhaps magnetism is the missing link. Although it's too soon to confirm whether magnetism is the key to understanding jumbos, it stands as one of the more compelling